The D-Hawk is a revolutionary new skateboard that boasts aerial, marine, and terrain capabilities. Preliminary designs of the D-Hawk resembles a standard skateboard body with tapered ends, two sets of triangular wings, and circular wheels. The D-Hawk is a newly imagined skateboard which will be able to fly alongside the operator when traversing hills and stairs that render traditional skateboards cumbersome or inoperable. The skateboard is able to float, and propel itself when submerged in water, allowing the operator to skate across lakes, rivers, and oceans. The high-tech wheels and suspension system standard in all D-Hawk models afford the operator all-terrain capabilities. The D-Hawk would be the premier mode of transportation in the event of a snowpocalypse. The all-terrain wheel system will conquer the slushiest conditions with plenty of grip to spare. The D-Hawk grants the operator the opportunity to explore the farthest reaches of our planet with impunity. Every few generations, a product comes along that changes the way humans live. This generation will be remembered for Google, the iPhone, and the D-Hawk.
We are undergraduates at the Georgia Institute of Technology. Georgia Tech is one of the most highly ranked and prestigious engineering schools in the United States. In 2014, U.S. News ranked Georgia Tech's undergraduate mechanical engineering program as third in the United States and second for aerospace engineering. The rigorous curriculum and considerable resources invested in student education allow Georgia Tech graduates to be the most sought-after engineers in the workplace. MECEE 1770 is an introduction to mechanical engineering, civil and environmental engineering, and aerospace engineering classes at Georgia Tech. The course introduces engineers to 2D and 3D modeling software, such as AutoCAD and Inventor, as well as modeling using hand sketches through isometrics and multiviews. The curriculum is designed in such a way as to introduce students to the product lifecycle. For a final 3D project, students are placed in teams that mimic actual professional engineering teams and are expected to complete tasks in a professional and timely manner. 1770 gives its enrollees a taste of the engineering process in the real world. It exposes them to the importance of teamwork, internal deadlines, communication, and responsibility. The MECEE 1770 class is taught by Professor Akash Dixit. Professor Dixit has numerous publications, patents, and honors in many fields. In addition to his considerable academic achievement and merit, Professor Dixit is also very passionate about giving back to the community, serving as editor to the International Journal of Aerospace Sciences and reviewer of the Mechanics Research Communications. For his PhD thesis, Professor Dixit worked on eigenvalue problems associated with discontinuous domain of self-adjoint systems. The first task the D-Hawk team had to complete as a group was the group proposal. Through the group proposal, we meticulously looked over the e-glide the previous groups had left us with. We found many glaring issues over engineering conventions and functionalities. We made changes to the defective sketches and inconsistent dimensions. Many parts had missing isometrics and/or multiviews, and many of the multiviews were not dimensioned correctly, or dimensions were inconsistent from one document to the next. After correcting the hand sketches, we proceeded to remake the final presentation video called Over a Cup of Coffee. We also met with Professor Dixit many times during this process to gain a sense of what he wanted us to accomplish with the group proposal. After we had finished Task 1, we proceeded to Task 2. For Task 2, we were able to start the redesigning process of the product lifecycle. First, however, we had to conduct a series of feasibility reports. The feasibility reports were separated into marine feasibility and flight feasibility. The feasibility reports dealt with whether or not the ambitions of the previous group for the e-glide were possible. Two functionalities of the board included the ability to travel on water and to travel in the air.
Hi, I'm Will Wagenseal.
And I'm Protik Das.
One of the first tasks we worked on was determining the feasibility of a flying skateboard. As Brandon said, this board is not meant to fly with the rider on it, but rather have it hover alongside the rider while he or she is walking uphill, or in any other situation which they don't wish to have riding the skateboard or carrying it. Since the board is meant to hover alongside their user, this board would presumably need to be able to maintain steady flight while moving at relatively low speeds. For this reason, the wings of the previous prototype would not be suitable because it would not be possible to generate lift at such low speeds. Instead, other methods of flight were investigated.
One method we investigated involved using vector thrust engines. This is a jet engine that emits a fast-moving stream of air. Rotating the nozzles downward causes air to thrust towards the ground. This in turn results in an equal reaction force upwards. When this force exceeds the weight of the payload, which is basically the skateboard, the payload lifts off from the ground. Airplanes that employ methods of vertical takeoff such as Harrier jets, use these type of engines. To implement this method of flight on the board, two rotatable vector thrust engines will be attached to the front and the back of the board. There are several advantages to this method of flight. First and foremost, the jet engines are very powerful and could therefore lift a very high payload. The engines are also less susceptible to weather conditions. However, the vector thrust engines are very bulky and require large amounts of fuel. This in turn could pose an issue considering since there's very limited space on the board, and therefore this engine could actually take up a lot of space and weigh a lot. The engines could take a while to warm up as well before the flight can be initiated, and they get very hot once they start up, which could pose a threat to the rider.
For these reasons, we looked at another method of flight. This was to use propellers rather than a jet engine. However, rather than use one large propeller, such as a helicopter would do, we looked at using 4 separate propellers. This is similar to the method a quadcopter would use. Essentially, the board would become a large quadcopter, and these propellers would swing out from the sides of the board, as we'll describe later on. This method of flight also has several advantages over the vector thrust engine method. First, the rotor blades can be powered by a battery pack rather than liquid fuel, which would be very large and heavy and would slosh around. Second, the quadcopter design is much quieter, and it won't have the heat problems that the vector thrust engine would have. However, there are some concerns with this method, the biggest of which is making sure the rotor blades have enough thrust and have the capability to lift the board off the ground. Ultimately, we figure we can still lift somewhere around 14 pounds with that size propeller. And this is an encouraging sign, and for these reasons, we are suggesting that we implement the quadcopter method of flight.
Hi, my name is Brandon, and for the feasibility report on marine, we conducted a series of tests. For the first part, we had to determine if flotation was possible. It was determined that flotation was possible and that there were 2 options. The previous group went with the option of a inflatable raft design that would be deployed once the water sensor inside of the board sensed water. The advantages of this system is that it is very cheap and it is very easy to deploy. Second option explored by the committee was the option of using a board with a material that was super lightweight, very buoyant, and also relatively cheap. The material we found to be most apt for this is cellulose. The advantages of using cellulose body are a sleeker design and lesser components in the board, which would reduce clutter and also reduce weight. The committee would recommend using a cellulose board instead of an inflatable raft due to these reasons.
Hi, I'm Ben Simon. Once we had determined that it was feasible to have a floating skateboard, we needed to come up with a way to power it through the water. Again, we looked at 2 possibilities. The first was the system used by the previous group, a jet engine powered by flammable fuel, and the second was some sort of electrical system, either a propeller system or an impeller system similar to what would be used on a boat or a jet ski respectively. We found that the jet engine had the advantage of having the highest maximum speed, but that was about the only advantage it had. Any electrical system would be much better in the respects of it would have lower maintenance costs and a much lower safety risk. So we eliminated the jet engine as a possibility. From there, we had to decide between a propeller system and an impeller system. A propeller system would have a large exposed propeller that would be connected to an electric motor and propel the board through the water. An impeller system has an internal propeller which is smaller and uses pressure to accelerate the board. We found that the impeller system was preferable because it would be smaller and would have no exposed moving parts. We recommend using an impeller over all of the propulsion options. I was put in charge of designing the impeller, and I'll show you how it works later in this video.
When the group was finished with the feasibility reports, we had a greater understanding of whether or not to continue with our present ideas. Some of the infeasible portions were halted in favor of the components that were actually feasible. During Task 2, we were able to begin redesigning the board. We also decided to rename it the D-Hawk. The first thing that made me interested in working on the D-Hawk was the notion of being able to design the flight mechanism of the board. Rotorcrats being one of my more favorite fascinations, I was very excited to be able to work on the design of the rotor wings. However, I had to go through certain complications when designing the basic rotary wing. We wanted the tip-to-tip length of the wing system to be roughly 12 inches, and that meant each wing was going to be about 2 inches wide at the widest and 6 inches long. At first, I considered drawing out the airfoils in 8 different sections of the wing by hand using the spline function. However, as you can see, they didn't go very well. Then I did some research on the website of the National Advisory Committee of Aeronautics, and they had an extensive database of different airfoil shapes that are used in helicopters today. As real as it would have made the rotor wings in our design, it would have required many more calculations and a much deeper understanding of airfoils to import these designs provided by the NACA. In the end, I decided to draw out the airfoils at 3 sections instead of 8, basically at the tip, at the root, and in the midsection, to make the design a little bit simpler, but yet clearly depicting the important shapes and features of the wing. I also designed the retractable arms that are going to hold the wings. These arms can go into the cavity of at the side of the board and retract in and out from there. At the tip of the arms, or palms if you like, there are hollows to place the motors that will be rotating the wings. We needed to rotate the arms 90 degrees out and back into the board, and to achieve this, we connected them to servo motors that were designed by my teammate Jonah Bergen, and he is going to tell you more about them next.
Hi, I'm Jonah Bergen, and I designed the servo motor that allows a quadcopter the capability of swinging out when needed to fly, so the rider doesn't have to carry the board. This was necessary in our design because we wanted the props to be stowed away while the rider is on the board but quickly deployed when the rider steps off. It's little designs like this which allow the D-Hawk to be widely accepted by the user because of its ease of use and diverse capabilities. The servo motor is a standard brushless electric motor. I decided to use a brushless motor instead of a brushed motor because brush motors use mechanical brushes to commutate the current in the motor windings. The brushes are in contact with the commutator and carry current to the coils. Over time, these brushes can wear out and introduce friction into the system. This does not happen with brushless servo motors. Most brushless motors need an alternating current source, or AC. For brushless servo motors, the construction of the iron core is turned inside out. The rotor becomes a permanent magnet and the stator becomes a wound iron core. The current in the external circuit is reversed as defined rotor positions. This allows for precise control of the motor and tighter rotations, allowing the motor to swing out the props and not to damage them.
The impeller unit provides thrust for the D-Hawk during waterborne operation. It is mounted on the underside of the board and works by taking water in at the front and forcing it out of the back at high speed and pressure. The front of the unit includes 2 large intake ports for water, as well as a watertight cover to protect the motor. The sides of the impeller taper in, which causes the water's pressure and speed to increase as it moves through the unit. At the far end of the housing is the impeller itself, which propels the water through a tapered nozzle and out the back of the unit. Power is provided by a 15 horsepower electric motor, which is connected directly to the impeller by a drive shaft. For safety reasons, the drive shaft is attached to the motor by a brass shear pin. If something becomes lodged in the impeller housing that prevents the impeller from spinning, the extra torque will cause the pin to break, allowing the motor to spin freely and preventing it from overloading or damaging the impeller.
Hi, I'm Andrew Hong, and I designed the marine steering system. The previous group utilized small motors and propellers in each of the wheels. The problem with this was the rotating joints would not turn due to the force of the water. Also, the system required many motors and complicated exposed wires that made the board vulnerable to damages. The D-Hawk utilizes a unique steering system that is both lightweight and motorless. To reduce the overall weight and the chances of the steering to fail, I made the steering purely mechanical. By taking out the motors completely, the banished power could be used elsewhere and reduce the chances of steering to fail. As for redirecting the water, for actual steering, I implemented a 3-rudder system. The steering is broken down into 2 bases, the front foot base and the rudder base. This allows front foot steering while keeping the rudder closer to the back. By doing so, the rudder will not shatter from the force of the water. Both bases were made of aluminum, which is lightweight and resistant to deformation. The 2 bases were connected by lightweight aluminum rods to mimic the mechanics of a 4-arm parallel lift. The reason the steering implemented this sort of steering over an alternative like gears was to keep the board as light as possible while keeping the board also as simple as possible. The two small aluminum attachment spaces keep the steering as light as possible and stabilize to the bottom of the board. The front base has a rubber grip adhered at the top to allow the rider to easily rotate the steering with his foot. Finally, the aluminum rudder has been broken from the traditional long rudder into three shorter rudders. The three smaller rudders allow the board not to be unreasonably high off the ground to keep the rudder safe from scraping on the ground and still maintain a bearable stress level.
Hi, I'm Yuzi Peng, and I designed the suspension system. Suspension is the system of springs, shock absorbers, and linkages that connect the vehicle to its wheels and allows relative motion between them. In this D-Hawk project, the suspension system is comprised of 7 different types of parts. First and foremost is the fastener, which is attached directly to the board by 3 screws. Connected to the fastener is the swivel, which rotates freely about the horizontal plane. Connected to the fastener by the swivel screw. Connected to the swivel are the 2 long legs, a connection facilitated by the 2 bolt screws. Lastly, the 2 short legs are the binding force for the unique type of motion facilitated by the suspension system. Each of the 2 short legs is connected to a long leg and the fastener via ball socket joints, allowing for a suspension system that naturally adjusts to shifts in the weight of the rider or differences in the gradients of the terrain. In order to improve the previous design, major changes were made to the suspension system by adding the springs and shock absorbers. In the previous design, all parts that were joined together to form the suspension system were rigid components. The geometry of the linkages also made it difficult to keep the board stability while steering or adjusting to the terrain. At first, I considered to apply the McPherson suspension system with springs and shock absorbers mounted vertically at the end of 4 long legs, but these additional structures would bring greater weight and water resistance. To give the board more reliable damping control while limiting the weight and making it easier to build, a spring and shock absorber were incorporated in each of the 2 short legs, which connect the long legs to the fastener attached to the board. As the rider steers the board on the ground, the springs are able to be compressed or stretched to decrease the vibration, and the shock absorbers give good control of the oscillation caused by the springs. The new short legs with springs and shock absorbers allows for elastic connection between the fastener and the long legs. This modification would make the board more capable of handling various road conditions and largely improve user experiences.
Tires are the key to a good skateboard, so I paid careful attention to how the tire design would act and feel. The previous group took the time and effort to make run-flat tires, like those on newer BMWs. While this seems practically sound for sustained off-road rides, last year's group made them too small in comparison to the size of the board to allow for a comfortable ride. The system was overly complicated and was too hard to scale up to fix this problem. I chose to redo the whole thing completely, starting from scratch. I started by researching what off-road skateboard wheels look like and why they are designed in that way. It became apparent that the diameter of the tire in relation to the size of the board was crucial in allowing for a smooth, bump-free ride. My final design is a simple off-road tire with thick rubber inflated tires and durable steel frame and bearings. The tread design is a simple V design which is raised well off the round of the tire to allow for grip and traction. Finally, I made the tire's diameter to be 9 inches. This increased the clearance of the board from last year's group and allowed for a smoother ride. This clearance was necessary because of the space acquired by the aquatic impeller, which is mounted on the bottom of the board.
The previous group utilized a rear foot strap to keep the operator from falling from the board. The foot strap was found to be too restricting and dangerous. The placement of the foot strap was also peculiar, as the operator was to be standing with one foot in front of the other and parallel to the board. The foot strap was located in the very back of the board, centimeters away from the jet engine at his feet. The foot strap design was scrapped in favor of a new foot plate design. The foot plate is a rotatable rubber plate 5 inches in diameter with a heel support in the back. Along the flat surface and along the heel support of the foot plate are friction strips that allow for maximum grip. The rubber also has a high coefficient of friction, ensuring that the operator's foot stays securely fastened within the foot plate and, by extension, the board. Our newly envisioned foot plate design allows for 45-degree clockwise and counterclockwise rotation. The rotation is accomplished through circular rails beneath the foot plate that are inserted to the connector. The connector is a steel plate that is sandwiched between the foot plate on top and the main body of the board on the bottom. In the middle of the connector are a series of elastic bands that provide resistance and gently guide the footplate back to its original position. This allows the operator the freedom to rotate while maintaining complete control and balance. The rotation mechanism is also a safety feature design in a sense that it seeks to place minimal stress and torque on the operator's ankles. The footplate is attached to the connector, which is in turn connected to the board through magnetic fasteners. The magnetic fasteners are inserted through holes in the connector into the magnetic fastener cover, which are embedded in set locations longitudinally along the board. This, along with the main rail, the two auxiliary rails, and the two complementary rails at the bottom of the connector, give the operator the freedom to adjust the location of the connector and, by extension, the footplate, to their own liking and comfort. The magnetism between the magnetic fastener and the magnetic fastener cover is supplied by an electric current originating from the battery. The electric circuit to the magnetic fasteners is cut when a button is pressed near the sides of the fastener. There are multiple fasteners to ensure that there are no accidental detachments of the connector from the board. The original design of the board also consisted of a safety pin that was to be clipped onto the rider. If the rider were to be separated from the board, the safety pin would dislodge and the power would be cut from the engine. It was a safety mechanism designed so that there would be no unmanned skateboard with a jet engine flying around. The design was scraped in favor of a new design that would rely on applied pressure. There are parts in the footplate assembly that depress when there is weight applied to them. In the event of the operator falling off the board while traversing on water, the weight would be removed and the power would be automatically cut from the impeller so as to prevent a runaway board on the water. This design was sleeker and less cumbersome than the previous design. It was also less likely to lead to accidental shutdowns of the engine due to the operators accidentally bumping into the clip and dislodging it.
At the rear and front of the board are small LED lights. Their design is based on the basic bike lights with the opaque plastic covering with a clear glass side. The shape is too thin to accommodate the skateboard's natural shape and not compromise any of its aerodynamic characteristics. Just like bike lights, these lights keep the skater safe at night by both lighting the road and notifying any cars or other vehicles of their presence.
Hi, I'm Reed Coker, and I designed the control system for a multi-purpose skateboard. I designed the control based off of various parts of the controller from a popular video game console named the Wii. The controller has 3 buttons near the base that read out water, ground, and air, right below each button. These buttons activate the features on the skateboard relative to the button name. To control the speed of the skateboard, a joystick is centered in the middle of the control and the word throttle is listed right below it. To see what features are activated in the current throttle speed, a small LCD display is right above the joystick. At the top right of the control above the display is a small power button. The controller runs off of 2 AA batteries that fit into a slot in the back of the control. To make the control watertight, the battery cover needs to be screwed in near the base of control. The battery power is also indicated on the LCD display. To increase safety so the controller will not be dropped, there is a hole in the bottom right of the control that allows a wrist strap to be used. The entire back of the control features a silicone grip to help you keep the control in your hand at all times. At the top of the control, an infrared sensor is used to contact the board to receive the inputs. On the left and right sides of the control, there are 2 clips so the control can be safely fixed in place in a compartment in the board while it's not being used. Overall, I want the control to be very simple, easy to use, and to have a familiar feel to its users. That's why many of the features are the same relative to that of the Wii's, since the majority of the consumers using the D-Hawk will be within that age group.
I was also in charge of creating the overall board assembly as well as the board frame. This meant that I had to carefully coordinate my parts with everyone else's parts and assemblies. The frame of the board itself is relatively simple. It has a rounded front and the back is tapered, but all in all it looks generally like a normal skateboard. There is a difference, however, in scale. This board is longer, thicker, and wider than your average longboard. However, given all its capabilities, this is understandable. The frame also had to have various cavities and extrusions on it to allow for the various assemblies to be attached to it. For instance, the sides of the board feature small rectangular cavities which hold the propellers and arms when not in use. The arms can then easily swing out courtesy of the servo motors when needed, but stay safely hidden otherwise. The board also had to link well with the rail system for the foot strap that Brandon described, as well as the steering, impeller, and suspension assemblies, just to name a few. As you can imagine, it was difficult to organize all these assemblies onto the limited space of the board. I ran into many issues during this process. The first involved the impeller assembly, which would shoot water directly into the rear suspension assembly based on the initial design. To solve this, a small hump was added to lower the impeller below the board further. Other issues I encountered included interference between the steering assembly and the impeller, and problems with components below the board that would likely scrape the ground. Anytime I ran into issues such as this, I had to contact the team member responsible for the respective part and work with them to make the necessary changes, and then update the system accordingly. Despite all the difficulties I ran into with regards to joining everyone's parts, we're very happy with the end result, which is an innovative skateboard with numerous integrated systems that all join together and complement each other nicely. And we appreciate the opportunity Dr. Disher gave us to work together as a team, come together, produce a final cohesive product, and really have a wonderful real-world experience.
We learned through this 3D project that planning was essential to any project, especially those involving multiple group members. Setting up meeting times was difficult because things would always pop up and hinder our ability to meet together as a group. Communication is also vital. We learned to keep a synopsis of what was discussed and accomplished at our group meetings. This way, group members who are unable to show up to the group meetings will still have an idea of what happened and not fall behind. We learned that these projects are not sprints. It is incredibly difficult to get everything done the last minute before the deadline. Not only would the work not be put to par, but it exhausts a great toll of the group members as well. This is where setting multiple mini deadlines comes to the rescue. It takes an initial investment of time to be organized, but it saves an exponential amount of time in the end. These smaller deadlines serve as a guide as to what each individual group member should have accomplished by now. These deadlines are purposely kept flexible to allow the group members some room to maneuver in the event of unforeseen circumstances. Planning ahead of time is crucial to ensure that all the tasks are completed by the deadline. I learned that different group members have different strengths and weaknesses. In order for the group to produce quality work, we had to help each other. The chain will only be as strong as its weakest link. If any team member has any special skills that are relevant to solving the problem at hand, be assertive and speak up, and communicate your expertise to the experience of the rest of the group. Ben had extensive video editing experience, so he took charge of editing and filming the 2 videos we had to create for this project. Many different leaders will emerge during this process. We were fortunate enough to have 2 aerospace engineers in our group, Proteek and Reed. They were able to advise us on the flight components of our skateboard. It is important that the group members listen to each other's ideas and concerns. If a conflict arises, compromise is important. For example, Andrew and I had a disagreement on where to place the arms that would move the impeller. The conflict was resolved, and the results speak for themselves.